Dear students, today we will discuss a very important topic of this chapter, that is your meter bridge. What is meter bridge? You remember, it is the practical form of Wheatstone bridge. You know what is Wheatstone bridge. So, meter bridge is a device used to determine the value of unknown resistance. Now, what is the principle of meter bridge? Principle, it is based on the principle of balanced condition of Wheatstone bridge. That is P by Q is equal to R by S. P, Q, R and S are the four resistances, are the four arms of Wheatstone bridge. Then, what is the construction? Before going to construction, you see the figure. In the figure, you see the wire SC. The wire SC, that is 1 meter long. Its length is 1 meter. It is made up of constantan or manganese having uniform cross section. You remember, constantan or manganese, they are the alloys. Constantan is the alloy of copper and nickel, and manganese is the alloy of copper, manganese and nickel. These alloys or these wires have high resistivity and low temperature coefficient of resistivity. High resistivity, it is understood. What is low temperature coefficient of resistivity? That means when you increase the temperature, the variation of resistivity is very small. And this wire, now come to the word meter bridge. Why is it named so? As we are using 1 meter long wire, from here you got the word meter. And as it is based on the principle of Wheatstone bridge, from here you got the word bridge. So here meter, here bridge. So the device is named as meter bridge. And this 1 meter long wire is fitted on a wooden board. Parallel to a meter scale. You see, it is a meter scale. It is 0 centimeter. It is 100 centimeter. That means the wire length is 1 meter. These are the thick copper strips. Thick copper strips. Why it is thick? Thick means width is more. You know, resistance is inversely proportional to area of cross section. If area of cross section is more, then the resistance is less. If resistance is less, then potential drop is less. That means along the copper strip there is no potential drop or negligible potential drop. That means potential at here is same as potential at here. Similarly, potential at here is same as potential at here. And you see, in the left gap of the strip, you have the resistance box. From the resistance box, you can provide resistance. If you open 10 ohm resistance then the resistance provided is 10 ohm. If you open 20 ohm key, then the resistance provided in the resistance box is 20 ohm. And here you see in the right gap you have the unknown resistance. Unknown resistance. By the help of this meter bridge, we will find the value of this unknown resistance. And between A and C, you see there is a battery with a key. And here is a galvanometer. One end of the galvanometer or one terminal of the galvanometer is connected to the copper strip at the point D, and the other end is connected to the jockey. What is jockey? Jockey is just like a metallic rod, and one end of that rod have the screw. You will connect the wire in this screw, and the other end just like a pointer. From the pointer, that pointer will move along the wire AC, and that determines the position of null point. Null point means no current flows to the galvanometer. Galvanometer shows zero deflection, or you can say that is the balanced condition. Now you see if it is the null point, this length let it be L, and this length will be, if it is L centimeter, it is 100 minus L centimeter. That means this resistance is, if it is P, it is Q. So now you just represent the whole diagram with a Houston bridge. You see it is A point, B point, C point, D point. It is P, it is Q, it is R, it is S, it is galvanometer. Between A and B, you have the resistance P. This point, this null point you take, it is B. Between A and B, the resistance is P. Between B and C, the resistance is Q. Between A and D, the resistance is R. And between C and D, the resistance is S. Between B and D, you have the galvanometer. And between A and C, you have the cell or the battery. That means it is just a Houston bridge. If the bridge is balanced, you know this condition is satisfied, that P by Q is equal to R by S. So, how can you write in construction part? You only write that it consists of 1 meter long constant tan or manganese wire stretched on a wooden board parallel to a meter scale, and this wire is of uniform cross section. The two ends of the wire are soldered to copper strips, soldered to copper strips. In the left gap there is a resistance box. In the right gap there is unknown resistance whose value is to be determined. One terminal of the galvanometer is connected to the copper strip at point D, and the other end of the galvanometer is connected to the jockey, which can be moved along the wire. The wire is fixed parallel to a meter scale, and a battery is connected between A and C through key K. Now come to working. Keeping key K closed. The jockey is moved till null point is obtained. Let L is equal to balancing length. Then what is the value of P? P is equal to resistance of wire AP, that equal to K into L, because resistance is directly proportional to length when wire is of uniform cross section. K is equal to resistance per centimeter of the wire. Similarly, Q is equal to K into 100 minus L. Now, balanced condition, P by Q is equal to R by S, or K into L by K into 100 minus L is equal to R by S, or L by 100 minus L is equal to R by S, or S is equal to 100 minus L by L whole into R, where R is equal to resistance provided in the resistance box. R is resistance provided in resistance box. So here R is known, L you can determine from the scale. Now putting this formula, you can find the value of unknown resistance. Also, you can find the specific resistance or the resistivity of the unknown wire. Resistivity or specific resistance of the unknown wire. You take L dash, length of unknown wire, and you take R is equal to radius of unknown wire, and you know the formula, the resistance S is equal to, you know, that is rho L by A. R is equal to rho L by A. Here we have taken S is the resistance of the unknown wire, so S is equal to rho L by A, or rho is equal to, here we have taken L dash, so we write L dash, S A by L dash, area of cross section, that is pi R square by L dash. So by using this formula, resistance value we have determined earlier, and R radius of the wire we can determine by the help of screw gauge, and radius we can determine by the help of the scale. So by using this formula, we can find the value of the specific resistance or the resistivity of the unknown wire. This completes your meter bridge. You remember, upon this concept or the meter bridge has 2 experiments in our practical syllabus. So let us discuss some questions on meter bridge, most important questions. Suppose in the lead gap you have one resistance, it is P, let it be R. If you question is, here we got R by S is equal to L by 100 minus L. My question is, if you increase this resistance to where the null point will shift, if R will increase, then from this equation definitely L will increase. That means the null point will shift towards right. L will increase, that means it will shift towards right. If S will increase, then 100 minus L will increase. That means it will shift towards left. Suppose it is the arrangement. If you add another resistance in parallel, then to where the null point will shift. If it is connected in parallel, then what happens to the net resistance? Net resistance will decrease. As net resistance will decrease, so if net means S equivalent will decrease, that means 100 minus L will decrease. That means it will shift towards right. So another resistance box, if you connect in series with the galvanometer, and if you are finding the null point at here, if you increase the resistance in this resistance box to where the null point will shift. If we will increase the resistance in this resistance box, then there is no change in the null point. Why there is no change in the null point? Because null point means no current flows through the galvanometer. If no current flows through the galvanometer, means no current flows through the resistance box. Already told, if no current flows through the resistance box or any resistance, you can ignore that resistance. That means you can ignore this resistance. That means null point remains same. That means if you change whether increase or decrease the resistance value in the resistance box in series with the galvanometer, there is no change in the position of the null point. Then is it necessary to connect resistance box? It is better to connect resistance box in series with the galvanometer. Why? Because suppose you are getting null point at here, but besides this null point at here or at here, some current is flowing through the galvanometer. If resistance box is connected to the galvanometer, if you are providing some resistance, then that limits the current. That means the galvanometer will not be damaged. That means by connecting resistance box or by providing some resistance to the galvanometer, we can protect the galvanometer, but it has no effect in the position of the null point. And another important point is that the sensitivity of the meter bridge is more if the null point is obtained at the middle of the wire, or we can say the error in the calculation of or in the determination of resistance is less if the null point is obtained at the middle of the wire. That's why we have to take the value of the resistances are of the same order. So this completes your meter bridge. In the next class we will discuss about potentiometer.